Andy Reiman, who's going to speak to us a little bit on app deconfliction, orchestrating distributed, multi-agent, multi-objective operations for power systems. And that sounds like a PhD dissertation topic that we would have. So a little bit about Andy is a senior electrical engineer, power systems researcher at Pacific Northwest National Lab, received his bachelor's degree in EE from the University of Michigan in Ann Arbor, and master's and PhD in electrical engineering from University of Pittsburgh. He has over 10 years of industry and national lab experience. He leads a portfolio of research projects in advanced distributed grid and grid edge operations, including software platforms, algorithms, and optimization. He's currently the project manager of GridApps project and also the team leader for system tools team for the distributed systems group and at BNNL. He also has a recent patent in 2022 on methods and systems for evaluating and improving distribution grid observability. So Andy.
Thank you very much. I will share and get started.
We can see your screen. If you want to make it full screen, we should be good to go.
Right. Am I missing presentation mode? 5 isn't working.
Can you go down to the bottom right to the little presentation?
Yeah, thank you. What a day. All right, thank you again. Right. Thank you, Noelle, for the introduction. Again, this presentation is on app or application deconfliction, orchestrating distributed multi-agent, multi-objective operations for power systems. I'm, again, with Pacific Northwest National Lab. I'm based in Richland on the main campus, so not too far from Pullman. I had originally wanted to come out there this week, but we, I guess, didn't get the logistics lined up in time. So thank you for bearing with me while I give this presentation remotely. As you may well know, we have main campus in Richland. We have satellite campuses in Seattle, Sequim, and Portland, Oregon, and we have a presence in Washington, D.C., and we also have lots of remote staff, especially since COVID. A little bit about me. I guess the introduction was fairly comprehensive, so I don't have to review my background too much, but in the middle is an overview of the types of things that I work on. So modeling and simulation, algorithms and software, and system architecture centered around grid edge and distributed systems. There's a picture of me and my family in the upper right. And then the projects that I worked on in fiscal year 23, which just ended in September. So GridApps is a large portion of what I do. And that is the project where the work that I'll talk about today comes from. And then a couple of other projects. The blue and red projects are out of the Department of Energy Office of Electricity, along with GridApps, also Office of Electricity. And then the yellow project there is out of the CEDO Solar Office of DOE. I have a couple quick slides on GridApps. And by the way, I had about 45 minutes of presentation. I will try to move faster since we started about 12 minutes late. So I will try to keep it to 35 to 40 minutes to save time for questions. And I don't know if you guys have a established process, but as far as I'm concerned, I don't mind taking questions as I'm presenting or at the end or both.
But I would suggest we do it at the end, just because we're starting a little late, and we can ask people to put them in the chat. And if we run out of time, we can still get your answers and send them to everybody.
Okay, perfect. Yeah, happy to follow up. And I'll try to wrap up by 10 till. So Grid Apps D is a platform for modular and distributed grid operations. The project has been going on for 8 or 9 years. We have a pretty well-established software platform. The vision is to create an ecosystem of interoperable applications. So the apps from Grid Apps D, sort of app store concept, except we would like it to be an open version of an app store concept. And the mission is to accelerate the deployment of advanced functionality. So that open application concept for distribution operations, to the extent that it exists and to the extent that we've demonstrated, allows new capabilities that might be developed by an independent app developer, allows those to be integrated with the platform relatively easily, and it allows them to be portable. So that helps break down existing silos in industry today. Grid Apps D has traditionally, and if you download it today, you'll still get one single platform, and it's downloaded through Docker, and there's a number of containers. But it's one platform, but we are working on refactoring to target specific stages in the technology readiness level hierarchy. We are working on a SDK or software development kit that will help app developers develop their apps, and then a test harness that will help app developers test their apps, as well as a field module that would allow us to replace the Grid Apps D simulation manager between the first two vertical rectangles there, the simulation manager and field emulator, we can replace with an actual field interface and have either an externally emulated field environment or an actual field environment for apps to interact with. And the app interface, the Grid Apps D API at the top, is the same throughout. So in FY23, and again, this just ended in September, the focus areas for Grid Apps D as a project were application deconfliction at the top. That was the single largest topic area that we looked at in FY23. We had an implementation of the distributed application API, distributed energy coordinator application, and then some technology adoption and engagement. Then in FY24, just to show some directionality here and where we're headed, we have some follow-up items on app deconfliction. We are working on characterizing computational attributes of distributed applications. We're working on, in the Grid Apps D testbed column from the previous slide, we're working on scaling that up so we can look at, right now when we look at multiple feeders, we look at a single GridLab D model under the hood, but we're looking at scaling that up so we can look at several of those at a time, up to the scale of a distribution system operator or a distribution utility. So dozens or hundreds of feeders once we're fully scaled up. And then we've merged the technology adoption and engagement into a single stream, but that's mostly semantics. Getting into application deconfliction, conflict occurs when we have multiple independent applications or apps that would like to control the same device set points. So we may have capacitors on the system, and we may have a VVO app that would like to control capacitors, and we may have a DERMS type app that's regulating reactive power and also has an interest in what the capacitors are doing. So we want to make sure that those two applications don't fight. So origins of conflict in distribution systems. First, distribution systems include apps that represent different entities. So we can have utility-owned apps that represent utility interests, and we can have customers and or third-party applications like aggregators. Systems are subject to a number of different mandates, including resilience, equity, decarbonization, and profit as a number of examples. It's not exhaustive. For example, reliability is in this group as well. But individual apps may or may not be aligned with a subset of these mandates, but not all apps are guaranteed to be aligned with all of these objectives. And balancing the objectives in the first place is a challenge as well. So different apps at the end of the day are likely to try to control different set points, have different preferences for what the same set points should be, unless they're fully coordinated and have been co-developed. But if they're independently developed, it's all but inevitable that the internal objective of one app will not be identical to the internal objective of another app. The approach of this activity, and by approach here, I mean the approach of the deconfliction task in the GridAppsD project, was to first identify a consistent formulation of a deconfliction problem. So we separate the gathering of application set points and the interpretation of application intent, and we look at basically a matrix of desired app set points. I'm jumping ahead a little bit, but a matrix of desired app set points consistently across no matter what approach we're using to solve that problem. Then we took the universe of potential solution techniques, divided them into rules and heuristics, inter-app cooperation, and optimization. I want to mention here that transactive mechanisms are another option for solving this problem. To solve a transactive problem, we need to be able to exchange or transact. We need to be able to exchange meaningful either incentives or utility or some means of deciding how much of one thing an app is giving to, how much of the thing one app is giving to another app in order to resolve this. But transactive solutions are not mentioned explicitly here. They overlap with any or all of these, maybe most similar to cooperation. But we divided into heuristics, cooperation, and optimization. And then we investigated each of these solution domains in parallel to identify strengths and weaknesses. And we ended up looking at multi-criteria decision-making, multilateral negotiation, and multi-objective optimization. And again, we did not consider transactive here. We have a fairly large transactive program. Transactions are useful if we're working across entities, but if we have different independently developed apps, each representing the same entity, it's not clear, how we're going to have one utility-owned app compensate another utility-owned app. And then step 4 here, combine elements from each solution to inform requirements for a deconfliction service. And the deconfliction service is one of the activities that we're taking on this fiscal year. So we did an alternatives analysis to look at that. This is a depiction of the standard matrix. I don't want to spend too much time on this slide. There's maybe a bit more math than I want to dig into, but this is conceptually a matrix where each application has a column, and the desired set point for each controllable set point in the system is represented as one of the elements in that column. And we allow don't care, so the double X's here represent don't care. Don't care means that an app's objective or success is truly independent of that variable. It's not as simple as did the app specify this variable or not, because in some cases, the outcome of an app will be affected by variables that they haven't actively specified. But setting that part up is part of the consistent problem formulation that I mentioned earlier. So we have a concept of a deconfliction pipeline that we're implementing in software. Starting with the application on top, applications specify set points. An application may or may not specify a set point if it wants, if it likes the status quo. So we have a set point processor that's job is to build that matrix on the previous slide and consider what what the app really wants, not just what the app is saying. So that's a topic that we haven't dived into completely, but we do understand and know that we need a solution to do this correctly for apps that we need to understand, does an app want the status quo or does it not care if the app hasn't sent a set point? And so we may look at the history of set points that the app has sent, and we may look at the types of parameters that the app is trying to control. For example, if it is trying to control reactive power using capacitors, then it has a stake in the reactive power control of inverter-based devices. Then the feasibility maintainer makes sure that the set points that get passed into the deconflictor are feasible from a device perspective. So if we have a regulator, voltage regulator that has tap positions between -16 and +16, we don't want to accept tap position of -18. Then the deconflictor, we have, again, multiple ways to solve this, and we're working on a deconfliction service that combines different ways to solve different elements of the solution domains to solve this. But the deconflictor block is where we convert that matrix of set points desired by apps into a single vector of set points that the devices will be controlled against. Then there's a validator block to make sure that system constraints are not being violated by the solution. And then a device dispatcher that sends the necessary device protocol based commands to have the devices track that set point vector. Solving the problem, I sort of alluded to this as I was going through the pipeline, but the input to the deconfliction problem is the conflict matrix, and that's standardized. Deconfliction solution uses a combination of one or more solution strategies. The solution, the deconfliction solver or the solution strategy can draw on optional information from applications. We don't ever require an app to send anything more than a set point, but some deconfliction solutions can achieve a much better solution if they do get additional optional information from the apps. And again, the output is a single vector that the devices will track. Here is an example using applications that are aligned specifically with one operating requirement for the system, so operational mandate. The left-hand app is trying to maximize resilience conceptually, and then we've implemented one interpretation of that conceptual objective in the block diagram below. Basically, if the batteries can be charged, this app wants to charge them so they're fully charged in case of emergency. And then if there is an emergency, it'll start to discharge them. And the app on the right would like to maximize decarbonization, again, conceptually. So here the app assumes that renewable energy is the distributed renewable energy is the best available from a decarbonization perspective. So it will always try to keep the batteries available to be charged when there's excess renewable energy, for example, excess PV during peak hours. And then it will always try to use that renewable energy as soon as it can once the peak goes away. Second choice for this app is the grid, and third choice is any fossil-based distributed, diesel generators, for example. So on the right, you can see an outage, the notch at in the evening here. But on the left, we've described 3 different basic deconfliction strategies. Resilience app exclusivity, so devices are controlled directly by the resilience app, and then decarbonization app exclusivity, same thing for the decarbonization app, and then a compromise where we simply average the 2 set points of the 2 apps. So we're not proposing these as viable deconfliction solutions, but we're by viable deconfliction strategies, but we look at how the system behaves when we do. And you can see on the right, the red trace is resilience exclusivity. So again, the batteries stay charged until there's an outage, then the batteries discharge during the outage, and once the outage clears, they start to charge again. And the battery may or may not serve the full outage. In this case, it does not. Then the blue trace is decarbonization exclusivity. So the batteries are kept available for renewable energy. At midday, there is some excess renewable energy, and that's used to charge the batteries. As soon as the excess goes away, the batteries are discharged to get that renewable energy back into the system, and the batteries wait for more excess renewable energy. And then the compromise, basically the batteries don't move unless the 2 apps in this case agree on which direction they should move. So they both agree that the batteries should be charged midday, and they both agree that the batteries should be discharged during that outage. And otherwise they don't agree. Here are some results, and I'll try to avoid getting bogged down here, but basically, we developed some success metrics that are shown in the top, sort of upper right, and the results are what you'd expect for the resilience exclusivity. The resilience metrics do well. For the decarbonization exclusivity, decarbonization metrics do well, and the compromise is in between the two. This may provide some intuitive insight into how we can balance these a little bit more fairly rather than just averaging, but that's for later. Getting into the parallel characterization of solutions, and these are less basic solutions. Q2 last year, Q2, that's number 1 here. Second quarter last fiscal year, we characterized each solution domain and tried to identify broad categories of solution techniques. And then after that, we demonstrated a particular solution of interest from that domain. So first we tried to map everything out, and then we picked one piece, one location on the map and implemented it. So first, in the rules and heuristics strategy, I apologize for the density of this slide, but if we focus on the bullet points and then the layers in the stack below, the particular solution that we implemented in this solution domain uses multi-objective or multi-criteria decision making. It sets up the problem based on operational constraints, and then it looks at system-driven criteria for success, and then simulates, basically using a particle swarm technique, simulates a bunch of different alternatives spanning the decision space for the controllable devices. The problem grows untractable pretty quickly if we have lots of different devices. So we also looked at distributing results, but either way, we create a set of alternatives, and then we evaluate each alternative using those system-driven criteria, and then we, using smarter technique, which is includes identifying alternatives, scoring them using criteria, and then it uses numerical rankings to create weighting factors for each of the criteria, and those are used to do a weighted sum of the criteria, and then we select the alternative, which is associated with a set of device set points that has the highest overall score at the end. The green layer is the procedure for that's described by the bullet points, and the purple layer is the smarter multi-criteria decision-making process. So here we showed results using decarbonization, CVR, and resilience applications. Again, the problem becomes untractable if we try to look at too many controllable devices at once, because the number of alternatives scales exponentially with the number of decision variables. And the results show that we, in the table, can distribute by switch area, by phase, or fully decentralized, meaning decentralizing by device. This, in this case, is possible to basically deconflict by device using this process, and which removes the combinatoric expansion. Deconflicting by device, we solve much faster and get results that are close to the final solution. So this shows how we can distribute the deconfliction process and still produce decent results. Next, we looked at cooperative processes for app deconfliction. Giving myself a time check, I wanted to spend 10 more minutes. So I'll try to calibrate level of detail accordingly. In cooperative deconfliction, we looked at cooperative theory using mostly business management literature. This includes negotiation and mediation. Cooperative deconfliction maps the different components of cooperative theory to different aspects of deconfliction, and then to solve basically the role of the mediator, and then the way that the apps interact can follow game theory or multi-criteria decision making again, or decomposition. So this is basically distributed optimization, decomposing the problem and allowing each app to take on a piece of the distributed optimization problem. Some results here. I'm going to focus on the takeaways here. So each solution technique resulted in success reduction from exclusivity. So if the application gets to determine exactly what everything does, that's exclusivity, like we talked about a few slides back. So each non-exclusive solution strategy resulted in lower success, but it increased the success metrics of other applications, which again is intuitive. If we're allowing the apps to use a portion of the resources, then they'll be better off than they would be otherwise. You can see the green trace in the plots on the right, tracking consistently in between the exclusive resilience and exclusive decarbonization results. The second takeaway, each technique will have varying degree of influence on the success of all participating applications, and I think that follows from the first one. Third solution domain was optimization. So we looked at using a centralized optimizer to solve this problem. And this can be broken down into two categories. First, if we just look at the green to blue to green process, the solid arrows. If we only have set points available, the deconflictor can basically find the optimal centroid of the set point requests, which looks like the compromise strategy from a few slides back if we expand that to an arbitrary number of applications. Alternatively, if the deconflictor has access to the internal objectives of the apps, then we can solve a multi-objective optimization problem. It's pretty invasive from an application perspective, and it's sort of reductive from ecosystem of apps perspective, in that we are reducing each app to its objective function, and then we're having a centralized optimizer decide what to do based on that objective. But it is one approach for solving deconfliction. So we looked at it. In this case, once we set up that multi-objective, so yeah, we looked at the version where applications supply their internal objective. Actually, the apps in this case supplied a utility function that is designed to mirror their internal objective, but the app can use whatever criteria it chooses to describe that utility function. So not quite as invasive as looking at the internal objective of the app, and more flexible because it supports apps that may have block diagram logic, for example, and aren't using an internal optimizer. But we're looking at a multi-objective problem at the end of the day, and we show results for different weighting factors at the bottom. So if we weight two different apps equally, we get the results on the left, and if we weight the resilience app higher, then we get the objective on the right, or the results on the right. So synthesizing all three solution domains, we took a look at not just the particular results that we just reviewed, but the full solution domains. We tried to break those down into elements, and we have 6 functional characteristics that we're looking for on the GridAppsD side. Basically, solutions balance app objectives, so they're not making arbitrary decisions. They're considering what the apps want. The environment of apps is dynamic, so apps can come or go. Apps are supported whether or not they actively participate. So earlier I mentioned that we don't ever require apps to supply anything more than the set points that they would have sent otherwise. So we want to support apps even if they're not participating actively. We don't want to just set them aside and say, you don't get a vote. Apps are black boxes from the platform perspective, so we're never going to assume that the deconfliction, that the platform or the deconfliction service designers understand what all apps are trying to do. We want the solutions to be scalable to a level of scale that is compatible with GridAppsD, and we want to be able to guarantee a solution. So on the right, we identified some criteria of solution elements that would reflect these characteristics of a deconfliction service. And we set up a table where we have the criteria from the right-hand column of the previous slide as column headers here. And the rows here correspond to the different elements of the different solutions. Yellow for rules and heuristics elements, red for cooperative elements, and blue for optimization. I won't go through the details here. Combining these, we look at a series of a cascade series going through each of the solution domains. So we look at rules to narrow down the decision space. Then we look at cooperation, trying to drive apps towards a consensus. So cooperative solutions get apps to change the set points that they're sending, and we want to allow apps to do that, and then we want to use optimization to close any remaining gap in conflict, which is essentially the role of a mediator in the cooperative solution. Very quickly, and I want to wrap up in 2 minutes, but this year we're working on implementing a deconfliction service based on the attributes that I breezed over in the previous slide. We're also looking at implementing or incorporating deconfliction with the GridFC distributed app architecture, and we want to look at some more game theory to try to improve the cooperative solution in a future Rev 2 of the deconfliction service. We still have auxiliary functions in the pipeline that we haven't fully explored or implemented robustly. We'd like to enhance the test harness with typical apps that can stress apps under test, and we would like to be able to do this at scale. We also are trying to show industry how to do this. And I think we're wrapping up here. These are the publications that we produced last year in this topic. These slides, hopefully we can make available soon. And if anybody's interested in any of this, please let me know if you don't have easy access to the slides. And here is the deconfliction team at PNNL. So everybody here worked on this and contributed results that went into this presentation. And with that, thank you very much. And we still have, hopefully, some time for questions or discussion.
Yeah, that was great. Thank you so much. And I see a couple cougs on that list on your team there. So I don't see any questions in the chat. So I wanted to open it up to, does anyone want to start with a question? It's muted. You guys are muted. So someone, okay, there you go.
Okay. So I was wondering about, you briefly mentioned the compromise between the decarbonization and the resilience scenario. And my question was, what kind of situation would that be implemented in? And is it always necessarily as straightforward as a compromise?
So what we meant here by compromise was simply averaging the set points on a per set point basis. So for each device set point, we take an average of all of the apps that are voting on that set point. So the word compromise was just a label for that procedure. I think this is a very basic way to solve this problem, and I think we can do better than that. And hopefully some of the solutions that we looked at later start to show us different ways that we can do better than that. Does that answer your question?
Yeah. Thank
Awesome,
you.
Thanks.
Are there other questions in the room? Not normally shy to ask questions in the room.
It all made perfect sense.
Yes.
Or I was too fast. Sorry if I was too fast.
I have a question. Like, you're trying to deconflict like different apps which are working together. And you're trying to, means whatever I got from the presentation was like you're trying to improve upon, like there shouldn't be a conflict of set points for devices from different operating apps. So can't we have a hierarchy of apps? Like this is how the hierarchy is, and if there is a thing that is on the higher hierarchy is what gets to set the device, like rest. And is that something that has been looked into, or it's like more complicated than I think?
So it sounds like there's two parts there. I'll address the second part, that app hierarchy first. Yes, we looked at an app hierarchy, and this is sort of, it's close to the way that industry does this now. If somebody's designing a platform from the ground up and designing all of the apps within that platform, then traditionally there will be one app controlling one type of device at one point in a particular point in time, and that app assignment might be modal. So if we're in emergency conditions, different apps might control different devices than if we're in normal conditions, or if we're in various types of alarm states, then we may assign different apps control over different devices. But yes, that's one way to solve this deconfliction problem. But we wanted to take a look at the bigger picture and look at all of the ways to solve the problem. The exclusivity strategy that we look at here is a form of hierarchy where we just assign all set points to a single app. And then if that app doesn't care about any particular set points, then other apps can look at the leftovers. But we want to do this in an extensible and generalized way. And I think if you're saying that there shouldn't be conflicts between apps in a well-designed system, I think that is likely true in a vertically integrated solution, but the world that GridAppsD envisions is one where apps can be developed independently. So you and I might develop apps on our own, and we might want to make the best version of those apps possible. And we may not be talking to each other while we're doing it. And as apps become more intelligent and get more access to more data, then you can start doing things like getting a small increase in behavior if your app that normally is dispatching capacitors, if it starts to look at voltage regulators as well, you can get some marginal gains by controlling additional devices. So the most advanced versions of apps will try to control basically all the devices all the time. And so what we're looking to do in deconfliction is start to unwind that and try to understand what does the app really care about, what is its core function, and what devices need the most say over in order to accomplish that core objective. Sort of a long-winded answer, but did that address your questions?
Yeah, but then doesn't it mean like you're trying to act as a central authority over the distributed nature of apps? Like
in some cases, yes. So the rules. Well, I guess first of all, we set up a pipeline where we are, we're in between the apps and the devices. So an app can't control a device without the deconflictor's permission. Some of them are more centralized than others. So the cooperative solutions try to influence apps and let apps influence each other, whereas the optimization-based solution is simply centralized optimization, solving the problem.
Yeah, sounds good. Thank you.
Thanks.
So Andy, I have a question, on your picture that had the four different areas, the chart, at the beginning there. Recently the National Academies came out with a new report on accelerating decarbonization in the United States, technology, policy, and societal dimensions. There's actually a seminar earlier today on that. I was just wondering, as we look at engineers, three of those we probably are really comfortable with, right? The decarbonization we can quantify, resilience we can quantify, economics we can quantify. So how do you see the equity part of this, particularly a big emphasis right now with energy justice and a lot of going on? How do you see that competing or interacting with the from an app side with the other areas?
Yeah, I think that's, thank you, a really important question. And of course, I'm an engineer, so I fall into the category of people that's comfortable with 3 of these and less comfortable with the one. But I think it's really important that we have multidisciplinary teams looking at this and looking at problems like this, because it is important, and the expertise that, so we have, as many of you may know, the team that I lead is part of the distributed systems group at the lab, and that's part of the energy infrastructure and buildings division. But within the distributed systems group, we have teams in renewable integration and system planning that have experts in equity and energy justice, and it's important to stay engaged with multidisciplinary teams. To give, and I am speaking outside of my core area of expertise here, but we're looking at, with one of those cross-cutting teams, we're looking at how equity can be considered from a system modeling perspective, and then a lot of the planning and operations activities that that we're used to are based on models. So if at the modeling level we can consider and build in attributes that inform equity metrics, if we can start to build some equity metrics that people are comfortable with, then we can start to operate along those lines. But it's always the energy justice experts talk about how like they might object to this this drawing and say, well, we don't want to consider equity and the other 3. We want to do equity informed decarbonization, equity informed resilience, and equity informed profit. My opinion is that you can do that with any of these, but that's the approach that they take. Again, long-winded answer, sorry about that, but does that answer the question?
Yeah, no, I think that's a great perspective as we look at this. And I did drop in for those online, the chat, the latest National Academies report. And we can provide that to those that are in the room as well, so that you have that. But, you know, I think there's a lot for us to learn as engineers on some of these perspectives. And I love your answer about really multidisciplinary teams, because we come at it at how do we solve the problem in numerical typically. And so how do we get people that look at some of the community impact? And there's a lot of talk about that in this report. So I think it would be beneficial and a good thing for our folks to look at. So, well, I think with that, we are out of time. Are there any other pressing questions? Well, thank you, Andy. We appreciate, we're sorry about the little mix up on timing, but appreciate you squeezing 45 minutes into about 35 minutes and then having a chance to have some time for questions. So, and we will get you up to Pullman sometime soon to interact with our group. So, well, thank you everybody for being.
Looking forward to that.
Thank you everybody for being here today, and have a great rest of your day.
Thank you all very much.